Welcome to part 4 of our Quantum in 3 Dimensions lecture. We were just about to start talking about the hydrogen atom. So let's think about our simplest form of the hydrogen atom, which is a proton and an electron separated by this distance r. So we're going to remain in spherical coordinates. So for our hydrogen atom, the potential energy that we're going to consider between these two objects is the Coulomb potential. So if you remember the Coulomb potential in spherical coordinates, we're going to have charge 1, charge 2. So we're going to have the product of the two charges. We're going to have the Coulomb constant, which we could write as 1 over 4 pi epsilon naught, which is the permittivity of free space. And we're going to have the separation distance, so 1 over r. The E here is our standard smallest unit of charge. That is 1.6 times 10 to the minus 19 coulombs. Okay, and so the negative sign comes from one of those E's being negative, one of those E's being positive for the proton's charge. So our Coulomb potential is just electrostatic attraction, and we're going to put that in the Schrodinger equation, the radial Schrodinger equation. So the radial Schrodinger equation that we just did an example on, we're going to write an h bar over squared over 2m. Don't forget our negative sign out front there. And we're going to have the second spatial derivative of this u function that, remember, was just r times our radial equation. So our variable r times our radial equation. We're going to throw in the Coulomb potential, where we had just kind of a generic potential in our Schrodinger equation. And then we're going to have that centrifugal portion of the effective potential that has to do with our azimuthal or our angular quantum number, our u, and then our allowed energies times u. So that is our radial equation for our hydrogen atom. So we want to solve this equation for that u as a function of r, and we want to use that to determine the allowed energies. So you may remember from quantum 1 that we had certain allowed energies for the electrons in a hydrogen atom. That's what we're doing here. Those certain allowed energies were actually described by the Rydberg formula first. So that was just a simple formula that a math teacher figured out that you could use to describe those different energy levels because they were observed experimentally. And then later on, the Schrodinger equation and the Bohr energies and everything that were figured out from the Schrodinger equation went ahead and showed that the Rydberg equation that described those energies was just coming from this stuff. So there's a little history for you. Okay, so we're going to use actually the same method that we used for the harmonic oscillator in chapter 2 to figure this out. So what's going to happen as with our harmonic oscillator, our Coulomb potential is going to allow two things. So this potential energy that we've put in the Schrodinger equation admits both continuum states. Right? So continuum states, those continuum states have energy that is greater than 0. What those continuum states describe is actually an electron being scattered away from the proton. So an electron escaping this orbit that I kind of roughly drew up here would be this first continuum state, or these continuum states. Our Coulomb potential also admits discrete states, which are the bound states. Right, we could call them either name. And for those are what we typically think of as our hydrogen spectrum, right? So those are the energies associated with the electrons that give us the photons as the electron moves between those states that we know as the spectrum of hydrogen, right? Okay, so let's solve both these cases. So if we start out here with our radial equation, we're going to clean up our notation. So we're going to clean up our notation with some simplification. We're going to throw in, again, a kappa that is going to be the square root of minus 2me over h bar. We're going to use that kappa for energies that are less than 0, so for our bound states, which means kappa is going to be real because this whole thing under this square root sign is going to be positive. So this is, again, for our bound states. Okay, so that simplification is going to allow us to take our previous Schrodinger equation. We're going to divide it by E. And so our Schrodinger equation becomes 1 over kappa squared times our second derivative with respect to r. And then on the other side, 1 minus me squared over 2 pi epsilon naught h bar squared, our kappa, and then 1 over kappa times r. We've got an L times L plus 1. And on the denominator, that's again a kappa times r squared. And all of that is multiplied by u. So there was a bit of algebra that went into that to go from this Schrodinger equation to what we have there, right? Okay, so we're going to simplify that even further. You'll notice in a couple locations there's this kappa multiplied by r. So we're going to simplify even further by introducing a variable we'll call rho that is going to be that kappa times r. Remember, kappa has to do with energy and mass and all that. And the mass in this equation, since we're describing our electron, the mass is the mass of the electron. All right, so we're going to use a rho that is kappa times r, and we're going to define a rho sub 0 that is going to be our mass, our charge squared, so that's our charge of our electron and our charge of our proton, the 1.6 times 10 to the minus 19 coulombs. That's our elementary charge, epsilon naught, and kappa here in the denominator. So these two things are two different variables. The distinguisher is that not subscript for one of the rows. Okay, so if we do that, then we can write that our second derivative, instead of with respect to r, but with respect to rho, all right, that's going to simplify this left-hand side. And we're going to have a 1 minus rho naught over rho plus L times the quantity L plus 1 over rho squared, and all that times u. So that just let us condense a lot of this stuff up here into just a couple of variables down here. And hopefully that will make our solving that differential equation a little bit easier. Okay, so the first thing you want to do is examine the asymptotic form of the various solutions that you might get. So you're going to examine what happens at the extremes. So at the extreme where rho goes to infinity, you're going to notice that rho naught over rho goes to 0. So it's well behaved. And also, oops, that should be a multiplier. L times L plus 1 over rho squared. So this term also goes to 0. So the asymptotic behavior of this differential equation is that as we head towards infinity, our second derivative just looks like our original function u. So the general solution for that, at least at this extreme, is going to be something like u as a function of rho equal to a e to the negative rho plus b e to the positive rho. Right? So if we look at that, e to the positive rho goes to infinity as rho goes to infinity. So we need to say that that normalization constant b equals 0. So our general solution then is u of rho is going to be approximately equal to a e to the negative rho for large rho. Yes? Okay, so it's that simple solution for our large rho. Okay, so that's our behavior at the extreme of headed towards infinity, which again, if we double check what we're talking about, we're saying that either the energy is getting very large in a negative way, or our distance is getting very large, right? Just to keep track of what we're even talking about. Okay, so then our other extreme is to look at as we head towards 0. So that could be our distance heading towards 0 or that kappa heading towards 0. So in that case, we can look at what happens to each of the variables here in this, and we can figure out that our differential equation heads towards something that looks like L times the quantity L plus 1 over rho squared u. And this is as long as we are not looking at L equals 0. So there's a footnote in your chapter that talks about this a little bit further. Okay, so if we're looking at that differential equation, that's yet another familiar differential equation, and we can come up with a general solution of that differential equation that is going to look like u as a function of rho. We'll give ourselves a different normalization constant, call it c, rho to the L plus 1 plus d rho to the minus L. Okay. And that would give us, if we threw that back into that differential equation, we could see that that's a general solution. So again, we are looking at the case where we're headed towards 0. And as this goes to 0, we see that this heads towards infinity. So our normalization constant d has to be equal to 0 for this to be a well-behaved solution, right? So our general solution really just becomes u as a function of rho being approximately c p to the L plus 1 for small rho. So we've got two solutions, two asymptotic solutions, and we're going to combine those for non-asymptotic behavior, so the behavior in between those two extremes. So if we combine those solutions, we are going to say that we're going to try out a solution that looks like u as a function of rho is going to be rho to the L plus 1 e to the minus rho. And then we're going to put ourselves, instead of a normalization constant a or c, we're going to use a v to the rho. And we want to find whatever this function is. So again, we've already done this for the harmonic oscillator, and what we ended up doing is a recursion formula and a ladder solution, the ladder formulas that we did. So you can guess that that's where we're headed right now. So that's exactly where we're headed. So if we're going to start out with our first derivative of this function, that's going to look like this. And I'm just going to shorthand my v as a function of rho as just v. Okay, so our first derivative looks like that. Then we take a second derivative, and it is going to look like this. Wait, there's more. So that's our first term. Then our second term is going to have a 2L plus 1 minus rho dv d rho. So this looks very messy, very ugly. A lot of terms there. If we want to write this in terms of this equation v that we're trying to find, our radial equation now looks something like this. So we have a rho, if we just move things around and rearrange. So we have a second derivative of v. We have 2L plus 1 minus rho dv dp, or dv d rho rather. We can pull out a rho 0 here. So remember, we defined that rho 0 previously. And that all equals 0. So we're going to assume that that solution can be expressed as a power series. We have a second derivative, we have a first derivative, we have the original function. We're going to assume that it can be expressed as a power series. So that power series we're going to write like this. And again, this kind of solution should look familiar from when we did the harmonic oscillator in one dimension. Oops, that should be a superscript, not a subscript. So that power series should be familiar with what we did before. So this attack should look kind of like something you've seen before. So now we just need these coefficients of the power series, right? So if we need those coefficients of the power series, we're going to again take our derivatives. So we're going to take a first derivative, oops, just a normal ordinary derivative with respect to rho. And for this case, we would get a j in front, a c subscript j. So this one's a subscript, this one's the actual number. And then rho to the j minus 1. And then our second derivative, actually before I go there, I should write this first derivative in terms of just renaming the index. So if we rename the index to j plus 1, we are going to do one of these. So I've got, still counting from j equals 0 to infinity, we've got, instead of j, j plus 1, c, that's a subscript j, plus 1, and then rho to the j. All right, so we just rename the index to go from here to here, which works out. Okay, so that's our first derivative. Then our second derivative, we're going to write in the same way. So our second derivative, we're going to say is and so we're taking that rewritten one where we've moved the dummy index to j plus 1 from j. And we've got rho to the j minus 1. So we're going to insert this into the radial equation. The radial equation that we had in terms of v as a function of rho. And we get something in the radial equation that looks like this. That's a j. So j plus 1, c, this is a subscript of j plus 1, rho to the j, plus 2 times L plus 1 times our first derivative. And that's a subscript j plus 1, and then that is rho to the j. And then minus, and this is our original function that we are guessing we can express in terms of a power series. So here's our original function that we are guessing we can express in terms of a power series. So all of that right there just happens to be this equation, now expressed with v as the power series, dv d rho as this power series, and the second derivative as this power series. So we put all that into this radial equation. All right, so when we do that, we're going to simplify, we're going to equate coefficients of like powers. So we're going to collect all the coefficients of p to the j, all the coefficients of p to the j minus 1, all of those coefficients, right? So once we simplify and equate those like coefficients, just like we did before, we're going to come up with an equation that looks like this. So j times the quantity j plus 1, c, now this is a subscript j plus times c subscript j. Hopefully those look different enough to you. Plus rho 0 minus 2L plus 1 c subscript j equals 0. So we come up with that big long equation, and again, that'll take us to a recursion formula. So we should be nice and happy with our recursion formula. This should look kind of familiar. That's going to give us that this coefficient c, j plus 1, can be had from doing this kind of math. All right, so I've got j plus 1, j plus 2L plus 2 on the bottom, and whatever this fraction turns out to be times the previous, so that's a subscript j, times the previous coefficient that we knew. Right? So that's our recursion formula. It gives our coefficients in terms of an initial coefficient. So we'll call that C0, the 0th coefficient. So C1, right, we would get from this stuff times C0. C2 we would get from this stuff times C1. That's our recursion formula. That's how we use it. Easy enough, should look kind of interesting. So let's double check that this actually makes sense with the solutions we found so far. So if we've got large J, right, we start getting high up in that indice, that would correspond to large rows. And C to the J plus 1 would start to look like 2J times J, or divided by J times J plus 1 times the next coefficient down, so C sub J. When we look at that, we could simplify that just a wee bit more and write it this way. So if that were exact, you would actually write that C sub J would equal 2 to the jth power divided by j factorial times our initial coefficient that we knew, the C sub 0, that we're building all these coefficients for. So if that were exact, our function that we said we could express in terms of a power series would be C0, count from 0 to infinity, 2 to the j power over j factorial, rho to the jth power, which you might or might not recognize that power series as giving you e to the 2 rho. So that means if we are expressing our radial solution, or the thing that's r times our radial solution, in terms of this, that whole solution looks like this. And that heads towards infinity as rho gets large, right? So if that heads towards infinity as rho gets large, that's exactly what we did not want. We were trying to make this behave itself at large distances. So what that means is what we did with our harmonic oscillator solution, that our series must terminate at some maximum value. So our series must terminate at some J max, we'll call it. Right? Throw another page number on this. So our series must terminate at some maximum value, just like it did for our last time we had a recursion formula, to get this to behave well at infinity. So that means that if you've reached your maximum value and you try to go one more, you're going to get a coefficient that equals 0. Okay, so if our previous equation for Cj plus 1, our recursion formula, gives 0 when we try to go one more, that means that we're going to take that recursion formula and we're going to say that when we put in whatever this maximum value is, we need to get a 0. And so what I'm really actually doing there, when I look at our recursion formula, let me grab the paper that has our recursion formula on it. I am just looking at this numerator and saying, let's set that equal to 0. And that means if we go one more, we're gonna hit 0, right? So if I'm looking at that and saying one more has to give us 0, that means we're gonna define yet another variable that we'll call n. That is this J max plus L plus 1 that's in those parentheses. That is our principal quantum number. Right, so that's the same n we've used before. So if that's the case, and I solve this formula for my row 0 has to equal 2n. So let's go back a couple pages. We defined row 0 as the mass of our electron, our elementary charge squared, over 2 pi epsilon naught h bar squared and kappa. And remember, kappa had to do with our energy. We are in our bound states, so we were looking at energies less than 0. So kappa is real because the things under this square root sign are going to be positive. And so kappa has to do with our energies. Okay, so if we do some algebra, we get an expression for our energy using this idea that we have to have a maximum value for our recursion formula to make this behave at the extremes. We're going to use that maximum value to define this principal quantum number in terms of that maximum value. And we're going to put it in here and here to get our allowed energies. So we get this formula that says our allowed energies are negative h bar squared, kappa squared, over 2m. If we put in what those things are, negative m times e to the 4th, so that's our elementary charge to the 4th power, we've got 8 pi squared, epsilon naught squared, h bar squared, times rho naught squared. Since we said that this has to do with what's allowed, what behaves at distances, our allowed energies are correlated with rho naught being equal to 2 times our quantum number. And so our allowed energies that we're going to denote with the subscript m, n that has to do with our principal quantum number, are going to be negative m over 2 h bar squared. We're going to factor this so that we've got a squared there on the outside, and 1 over n squared. Now we could define a ground state energy that has to do with, or a ground state energy that has to do with this set of things in this square bracket. Just call it E sub 1, and then over n squared, and n is going to be allowed to be 1, 2, right, any integer value. This right here, this allowed energies equation, that is the Bohr formula. Right, and so the steps from n equals 1 to n equals 2, or n equals 2 to n equals 3, and so on, are this pattern that Rydberg came up with, and then Bohr's formula matches Rydberg's pattern that he saw in the spectrum of hydrogen. right? So in terms of this, we can write kappa as being m e squared over 4 pi epsilon naught h bar squared times 1 over n. We could define all that stuff in the parentheses as A. So A is the Bohr radius. And A equals the inverse of the things there in the parentheses. So m e squared. And remember, m is the thing we're talking about that's in orbit. So in this case, it's the electron. I think there's a problem in your homework I assigned that has to do with kind of a different kind of particle where it's not an electron in orbit, but mu electron maybe, I'm not even sure. But it has a different mass, and that's where that comes into play, is in the spots in these equations where you're talking about mass. It has the same charge, different mass, right? So A is our Bohr radius, and then our Bohr radius we can figure out with our standard electron values. So for hydrogen anyway, is going to be about half of an angstrom, right? So that's kind of your size of the hydrogen atom that you know about. And then of course, in terms of all these things, the rho that we defined, we can write as our R value, right? That's our just spatial location R, divided by our Bohr radius times our principal quantum number, right? So we can get our spatial wave functions for hydrogen labeled by these different quantum numbers, right? Just like for our example solution. Let's write that down. So our spatial wave functions for hydrogen is what we're going to be talking about. These spatial wave functions for hydrogen are labeled by our quantum numbers L, M, and N. So first by our principal quantum number, then by our azimuthal quantum number, and then by our magnetic quantum number. We're still in spherical coordinates, so we'll label that. We've got our radial solution that we need both N and L to help us describe. And we have our angular solution, which we've already solved for. We need both L and M to help us describe. And that's a function of theta and phi. All right, so if we refer back to our previously worked solutions for all of these things, the radial portion of this, which again, we need N and L to help us describe, is 1 over R times rho to the L plus 1 power times E, and this is E as in our natural number, not our charge. That's not confusing. To the negative rho, and then this function of rho. And that function is a polynomial. Of degree n minus L minus 1. Hopefully that's legible. So it's a polynomial of this maximum degree, and it's a polynomial in rho. So the coefficients of that polynomial are given by the recursion formula. that we figured out. So our coefficients are given by c to the j plus 1, or that's our subscript. We've got 2j plus, should be j plus l plus 1 minus n over j plus 1, j plus 2l plus 2, and all of that multiplied by c sub j. So that is up to our normalization factor. All right. Then in our ground state, so this is just a summary of what we've already done. Our ground state tells us, ground state is where n equals 1. So our energy of our ground state is negative m over 2h bar squared and so the negative ground state energy of hydrogen, it's negative 13.6 electron volts. If we do that in terms that will give us electron volts of energy. The negative energy comes from us saying that energy equals 0 is the border between a bound state and a scattering state. So sometimes this ground state energy is called the binding energy. So what that means is that if an electron in the ground state is bound to our hydrogen atom, this is the amount of energy you would need to impart on that electron to free it. So you would need to add 13.6 electron volts to an electron in the ground state to ionize that hydrogen atom, right? So because we defined our principal quantum number in terms of where this recursion formula maxes out, if n equals 1, you have to say that L equals 0. And because our m quantum number is dependent on our L quantum number, m also equals 0. And so our ground state wave function looks like 1, 0, 0, because that's what's allowed in terms of how we defined all these things. And you would look at a radial formula that has to do with 1 and 0 for those two quantum numbers, and the angular formula that has to do with 0 and 0. And so you would use the recursion formula, only the first term surviving, that C0 survives in that recursion formula. So your radial formula only has that first number, and this is your ground state radial function. Now, once you have that ground state radial function, that C0 you would get from normalization, right? So our next step would be to normalize. Normalized, not normalized. So if we normalize that function I just wrote, remembering what our normalization conditions are for spherical, we have this extra term. We get something that looks like this, and this is saying that it exists in all R. So from 0 to infinity in R. And we would have to integrate this. That integration would give us this C0 squared A over 4. And we would want to set that equal to 1 for our normalization condition. So if we set that equal to 1 and we take the positive real root, we're going to say that our normalization constant is just 2 over root A. And A is, of course, our or radius, right? So there's a lot of terms in that A. And then if we look on our table of our angular formulas, remember we have to use the Rodriguez formula and all that fun stuff. We find that our angular equation is simply 1 over root 4 pi. So our ground state of hydrogen we've found the ground state wave function to be principal quantum number 1, angular and magnetic quantum number 0. And of course, this is a function of r, theta, and phi. Just was too lazy to write that down. We've got pi a to the 3rd under the square root sign here, and then e to the minus r over a. So that is our ground state of hydrogen's wave function. Now we can go a step further. We can say, if we go into the first excited state, remember our energy formula looks like this. So our ground state of energy divided by n squared. So in this case, ground state energy is negative 13.6 electron volts. 2 squared is 4. So in this case, we've got a negative 3.4 eV. So this is our first excited state. But don't let the first fool you, n equals 2. So in our first excited state, we can have 2 cases. Either we can continue with L equal to 0 and M must be equal to 0, or we can have L equals 1, because L can equal 1 less than N, right? And if that's the case, M could equal 1, M could equal 0, or M could equal negative 1. So we actually have 4 states folded into this first excited state, right? Okay, so for all of that, let's start with our first possibility. Let's start with the easier case that L equals 0. So our recursion formula gives us this case, that C1 equals minus C0 for J equals 0, and then C2 equals 0 for J equals 1. Right, so then that placeholder function that we have in our solution gives us C0 times 1 minus rho. That's our polynomial of that degree. And again, so that's our power series. And we're going to throw this into our equation for our radial function. So our radial function for n equals 2, L equals 0, as a function of r, is going to be C0 over 2a times the quantity 1 minus r over 2a. And that is coming from substituting in for rho equals r over a times n, right? And then e, it's our natural number e, not our charge, over e to the minus r over 2a. Easy enough. Okay, if instead we look at the next case, we're going to see that that function is constant, and r, where our principal quantum number equals 2 and L equals 1 is going to look like C0 over 4a squared times r times e to the minus r over 2a. Again, our C0 is determined by normalization. And it's not necessarily the same C0 as in our previous equation, right? So that's something you need to determine each time, and you can't assume that it's the same for all of our radial equation. For our arbitrary n, right, so we looked at the first excited state, but we can picture that there are many more states that we could be solving for. So for any arbitrary n, you're going to have possible values of L that are going to range from 0 all the way up to n minus 1, right? And then for each L, you are going to have values for m that range from negative L through 0 all the way up to positive L. So you're going to have 2L plus 1, that extra 1 is the 0, possible values of m. So you can picture that there are going to be some states that might have the same energy level. So like I said, for the first excited state, there's this one allowed energy, but we have 4 ways we can describe that state. So you would say that these different states, these different wave functions with the same allowed energy are degenerate. And the total degeneracy of any one of these states is going to be given by a simple formula. And this is just coming from the allowed values of L and the allowed values of M. So the total degeneracy actually works out to be n squared, right? So we saw in our first excited state where n equals 2, we had 4 possible states. Where we go to n equals 3, we're going to have 9 degenerate states with that same allowed energy. Our polynomial that we're using here, that v as a function of rho, can be written apart from the normalization in terms of Laguerre polynomials. So I'll write that down for you. So polynomials with this subscript and this superscript where that capital L to the Q minus P in the subscript and P in the superscript is a function of X. So these are Laguerre polynomials. And they are defined in this way. Oops, that should be a dx. So this should be an x here, not the q I originally wrote. And this is the qth Laguerre polynomial. So we have a recursion formula to help us, and the summation to help us find our polynomial function that we're using here. But there are entire tables of them that we could also look up. All right, the first few polynomials like this are found in a table in your book. And in general, we could write our wave function in terms of a formula. I will put it down here right there. I'm not sure, but here is your formula for your spatial wave function in terms of things like n, your quantum number, a, that Bohr radius, l, your azimuthal quantum number, and m, of course, is in here in your angular function. So there are polynomials within this solution. There are polynomials within this solution as well. So your wave functions depend on n, l, and m. That is an oddity of the Coulomb potential, that the energies only depend on n alone, right? So that is kind of interesting. Now your wave functions are mutually orthogonal. So you can check this, that if you take n, l, and m's that are different from each other and do this check, you will get the Dirac delta for all of them. So they are mutually orthogonal. This is coming from the orthogonality of spherical harmonics. So when you have different quantum numbers in there, you're going to have the fact that they are mutually orthogonal. And they're eigenfunctions of our Hamiltonian with distinct eigenvalues. There's some visualization of this in your book. Let me flip to that and share it with you. So this visualization of, at least I think there's visualization. This visualization of our wave functions we can see in density plots. Right, so there's some density plots with the where they've come from. And it's not surprising that these look like the orbitals you've seen in possibly chemistry. Here's another visualization of those harmonics, right? So if we zoom out on that, right, that is another visualization of these things in 3 dimensions. And those are the spherical harmonics, and they're mutually orthogonal. That seems like a good place to stop this one. We'll continue on at this point in the chapter next time.